Hi, I'm William Bushy, and this is Physics 2, Lab 4. So this lab is to demonstrate how energy, in this case as electric potential, changes with various circuits and their components. These components include nodes, resistors, and capacitors, and how we can predict the change in energy via these components. So here are some equations and constants we're using. The loop rule, which in a closed circuit, the sum of all voltage differences across the circuit is 0. At a junction, the total current between two branches equals the current before the node, which is the node rule. There's Ohm's law, which is voltage equals current times resistance. For capacitors, voltage equals charge over distance between plates over E naught times area of the plates. Capacitance C equals charge over voltage, which equals E naught area divided by the distance. In the lab-specific equation, the natural log of the voltage difference over the initial voltage potential is negative time over RC for charging capacitors. V of the batteries we used in the first part of the experiment is 3 volts total. The R total is 147 ohms for this first part of the experiment, and the R of the wire is delta V over I, which is 0 over 0.02, which equals 0. So here's the first part of the experiment. 2 batteries, each of voltage 1.5 volts, were connected in a circuit comprised of wire and 2 resistors of R equals 100 ohms and R equals 47 ohms. Ammeters were placed before and after the resistors in a series, and the current was measured when a voltmeter, and the current was found to be 0.02 amps. When a voltmeter was added in parallel, the same circuit was observed as the same as when the ammeter was quote-unquote backwards. So the voltage difference for the 47 ohm resistor was 0.959 volts, and for the 100 ohm resistor it was 2.041 volts. So observations that were made were: why doesn't the voltmeter change the current? Its resistance is so high, it's almost as if the electrons aren't moving through it at all. What happens if you connect an ammeter in parallel to the 100 ohm resistor? Both ammeters read 0.06 amps, as the electrons flowing through the parallel branch only experience resistance from the 47 ohm resistor, and 3 volts over 47 ohms is 0.063, which is roughly 0.06 amps. And once again, here are the resistance of the various components. Here's some more observations. When a bulb is added in a series to an RC circuit, it lights and slowly dims until light is no longer emitted. The same thing happens when connected directly to a capacitor that has been charged. This is because the current slowly decreases as the capacitor is charged, and thus there are no electrons flowing through the resisting bulb, so there's no change in voltage represented by loss of energy as heat or light. For bulbs of differing resistance, the capacitor took longer to discharge. For a 10 ohm light bulb, it was 9.4 seconds. For 20 ohm bulb, it was 18 seconds to discharge. Here's the data of how long it took with a 30 ohm light bulb to reach certain voltages. As you can see, it slowly tapers off and is thus a logarithmic scale. And if you apply the lab-specific equation, you can linearize it and show that the natural log of the voltage differential over the initial voltage differential is the negative time over resistance times capacitance. So that is how you can calculate how quickly a capacitor will charge. And if we had used an actual ammeter instead of ideal, there would be current flowing through the ammeter and resistance would be decreased, increasing the overall current of the system. If there was a battery connected to a capacitor in real life with no resistor, the prediction that V over V naught is negative T over RC would rearrange to be T equals negative VRC over V naught. And with a resistance of 0, it would be instantaneous, supposedly, which is not possible because even if minute, the wire has some resistance.